Hello everyone, and welcome to the first lecture of the online lecture series of Motion Control Systems class. As you might all know, our faculty has moved to the new schematic until this coronavirus emergency actions pass away or fade away. So I hope all of you are healthy, all of you are staying at home, and all of you can follow the video series I'll be recording. Now the new methodology will be in, with the new methodology will be covering the recording of lecture notes. Actually, I have two cameras. I'll be moving to the other one, and I'll make the derivations on a paper. You can watch them out in the YouTube channel, and I'll provide you with an email at the end where you can ask your questions, and I'll try to address your questions the best way I can regarding the motion control systems class. Well, if you remember last time we have derived the force observer structure, and we have shown the position control, velocity control, generalized error control, and after deriving the disturbance observer and reaction force observer schemes, I've told you that that is kind of the end of the first section of motion control systems class. And now we're going to start a new chapter, a new era. And today's lecture will be about force control. So I'll move to the other camera and I'll make the derivations for you on a paper. Let me change the source. Okay, I hope you can see the lecture notes here. Let me mark the page number. So, today's lecture will be about force control. If you remember, when we were talking about the structure of force, I was telling you that the force we intend to control here is the interaction force. So, interaction force occurs when there is a contact with environment. So that exists if and only if there is contact with physical environment. So let us now slowly move towards the analysis of what different kinds of environments we might encounter when trying to control the force in a robot or in general in a motion control system. So let me, by the way, highlight this as the lecture topic of today. First, types of environment. It's important to have a look at this word here, environment. Without loss of generality, any kind of medium where a robot interacts with is called environment. So that is the medium with certain physical properties. Let's slowly move towards the topic. Assume that I have, okay, let's go through an example. Assume a single degrees of freedom motion control system. Now, let's try to depict the system. Okay, suppose that you have a motor here and your motor has a rotating arm, okay, that can rotate this way. Okay, that's your motor, and at the tip of the arm there is some hard metal, and you're trying to interact with an environment here. So the force exists if and only if there is contact, physical contact with this environment. Okay, so let us have a look at the properties of that environment. So usually there is a standard impedance model for the environment. When you deflect this environment from its natural position, let's take the model here with certain deflection. First of all, it's obvious that you displace certain amount of mass here. Okay, so this has certain mass properties, and the deflected environment behaves generally like a spring and damper system with coefficients K and B. And the resultant force can be given as delta M. If you put here the deflection as the, okay, let me mark this point as x naught, and this is your x environment. Delta M, x environment minus x naught double dot plus B x environment minus x naught dot plus K x environment minus x naught. So if you ignore these two components and only have a look at this part, this is simple standard spring model, right? But not only, I mean, not all of the environments are consisted of pure springs, but some of them include the damping. Damping is the property of environment that loses a certain amount of energy. So let's move to the second page. I hope you can see there is a problem with, okay, now you can see it's focused. So we will be starting by the simplest assumption. Okay, start from simplest case. That is, if the environment is assumed to be a pure spring. Well, with this scenario, your force input to the environment the force generated at the contact point will be governed by pure spring equations, the environment stiffness times the deflection in environment position, x minus x environment. Let me put here x naught, that's the original position of the environment, and x environment is the point where you deflect. Let me mark them x naught, and here you have x environment. That's the total deflection. If your force is given this way, how can you carry out the control? So recall, in order to control the force here, we need, so for controlling the force, we need to have a reference, and from which we can generate an error. Okay, let's assume that, okay, given f ref as twice differentiable continuous force reference. What do I mean by this? Twice differentiable means that f ref exists, f reference dot exists, and f reference double dot exists. You can differentiate it 2 times. Okay, well, obviously the control error will be f ref minus f environment, right? So we can call this to be, so let's define this to be EF, force control error. Now, EF was force reference minus F environment. Well, let's go back to the original definition of environment force in the simplest assumption and try to substitute it to this equation. If you remember, F environment for the simplest case was taken to be K environment, the environment's stiffness, spring constant, times the deflection created in the environment, right? So I can write here X naught minus X environment, right? Well, with this scenario, I can take that equation and this equation and write it as EF, the force to be controlled, the force error to be taken to 0 value, is equal to F reference minus K environment times X naught minus X environment, right? Well, let's give here some marks. Let's make some simplifications. If I assume that the motion control system is already in contact with the environment. So let me take this as a granted assumption. I'll try to analyze the cases with you when there's no direct contact with the environment and the initial position is starting from a point without direct environment contact. But let's, for the timing, let's assume that initial contact with the environment is already established. Okay. And the second is, of course, if we take it this way, XE, the deflection created in the environment, will be equal to our system's response motion, right? XE will be equal to X response. What I mean is something like that. Okay, let's assume that the same single degree of freedom motion control unit is already in contact with my environment. Actually, this is not a good example to give, because we're talking about linear items here. Let me mark this and move to the next item. So xe is equal to x response. We can better exemplify this if we assume that we have a linear actuator. Okay, so that's like a linear motor that is already in contact with our environment. Okay, so that is the environment. In this scenario, since the initial contact point is the initial position of the motor, and since the motor's deflection will be equal to the environment's deflection, this assumption will be valid. Let's move on with this. So we had, that's the fourth page. I hope it will be okay. Well, there's a problem with the zoom, with the focus of the camera. Let me change the source. Okay, from this, deactivate and then activate again. Okay, it's focused. So, all right. So, what we had was this. We had the error, the force control error, to be taken to 0 value, which was given as the force reference minus K environment times X response, if you remember, right? So, if you remember, let's write here, recall. What we were trying to do was to push error in such a dynamic scenario where it goes to 0 value regardless of its initial value. If you remember, we were able to do this through differential equations, and here we have the x rest, so we have first order system. There's no velocity component here in that equation, right? If you recall from the pure position control, an equation in this form has to be differentiated 2 times so that we can extract the desired acceleration, that's the response acceleration for a system with disturbance observer. So that was the first item, and let me put here the second item. Try to extract the response acceleration, so that was named as the desired acceleration, so that in such a way that a system with disturbance observer can trace this acceleration. So For that equation, let me highlight it once more. I'm sorry, okay, here's it. Let me highlight it once more. For that equation, we need to differentiate twice. So EF double dot plus alpha times EF dot plus beta times EF is equal to 0. So that equation is, it was a key equation for pure position control, if you remember. And we will apply the same equation for the force control again. Okay, let me also change this. Okay, now let's take that equation from there and substitute it here. What will we have? So we're basically going to get this F reference double dot minus KE X response double dot plus alpha times F reference dot, don't forget the derivative here, minus KE times X response dot plus beta times F reference minus KE X response should all be equal to 0. That's the main equation that we have in hand. So in this scenario, it's not so difficult to extract the desired acceleration from the response acceleration. So what this equation tells me is that, assuming that my force tracking error is that, which is the reference force minus the environment's force model, and assuming a second order dynamics where we have two parameters, alpha and beta, we already analyzed them, but I'll make a recap of this here in this video. The second order dynamics applied on the force given there, force error given there, will yield to that equation. Extracting the response acceleration from this equation and writing it down as the desired acceleration for a system with disturbance observer would yield to the force control algorithm, mathematical algorithm for force control. So without loss of generality, we can move this to the right hand side of the equation and divide everything by KE to get this X double dot desired, which is nothing but X double dot response in our case, is equal to 1 over KE times F double dot reference plus alpha times F dot reference plus beta times F reference minus, I have here alpha KE X dot response. So let me put it here. So minus as a whole alpha KE X dot response plus beta KE X response. So we now have our force control algorithm. The desired acceleration is equal to 1 over KE times the force dynamics minus the feedback from the system. Of course, this is only valid when you have a properly working disturbance observer in your system. Let's try to draw a picture. Let's try to put this equation in a block diagram. I'll do it in the next page. So let me see if you can see the whole page. Maybe you cannot see it as a whole, but I'll try to show you in a wider screen. Well, now we have here force reference. Once again, the resolution of the camera is gone. I have to change this. Sorry for that. Deactivate and activate again. Okay, now you can see it. Here's your force reference. It goes directly, it goes with a coefficient of beta. So F dot reference goes with a coefficient alpha, and F reference goes directly, so we can actually add them up. This is the left half of the equation inside the parentheses. So F double dot ref, alpha F dot ref, beta F dot F ref. Oh, I'm sorry. I should have beta F ref. F ref, that's okay. There's no problem here. That's my mistake. That should be F double dot ref. Well, is there any way to change this? Let me try to draw it for you from scratch. So you have here F double dot ref, F dot ref, and F reference all together. So F double dot ref goes directly. F dot ref is scaled by alpha, and F ref is scaled by coefficient beta. All of them are summed up at the summation point. So this is that part of the equation. So from this I need to subtract the feedback side. So put this as a whole and use a minus sign to subtract alpha ke x dot response, beta ke x response. So I can call here the signals. So alpha ke, that's a scaling factor, and I can write here beta ke, that's another scaling factor. So I can add them up here, and they should be subtracted from the feedback loop. Of course, these are alpha ke times x dot response, beta ke times x response. These are signals obtained from the response of your system. So altogether they should be scaled by 1 over ke, and then this gives us the desired acceleration. If you remember from the previous equation, let's go back. It's here. X double dot desired is equal to 1 over ke times the force part minus the feedback from your system. And you can give this as input to your plant, with disturbance observer. I'll not draw the entire disturbance observer structure here, but since we have covered this in the previous lectures, you know what this is. And of course this plant will yield to several outputs. maybe x double dot response. Here you have x dot response, and here we have x response. I think we can simply take x response to be connect with this, and we can take a feedback here and connect this that way. So this is our overall control block diagram. Now, you might ask several questions actually on this scheme. First of all, the very first question that pops up in my mind is whether an environment with pure spring constant is a valid assumption or not. Second is force structure. Do we always have these? And third is about the measurements. Well, let's start with the simplest one. It's easy to take the response measurement from a plant through an encoder. That's the easy part. The response velocity of the plant, that's the response speed, response velocity of your motor actually, is easy to calculate once you have the response position from your plant. And if you see, we're not making use of the response acceleration of the plant here. We have covered the structure of how to implement the disturbance observer on a plant. It's not also difficult for us. Now, these are simple scaling gains. Let's have a look at the force structure. In industrial applications, most of the time, you either have a set point force reference, which means that your force reference exists, but F dot and F double dot does not exist because it's a set point reference. What I mean by set point referencing is that if you have like a step function, some f ref value, so if your f ref value with respect to time is given as a step function, you don't need to calculate f dot and f double dot ref. It's easy. But sometimes your force profile might be given as a continuous and differentiable. So this is actually f ref. So that's over time. Continuous and differentiable function. So if you have this, of course, you need to calculate f dot ref and f double dot ref. And it's not too difficult because that's what you are giving to your system. So you want to have this force profile to be traced in your system, and it's easy for you to calculate the derivative and second derivative of those signals, of this signal. Well, validity of the spring environment. It's not too difficult to claim that majority of the existing robotic applications make use of similar application, assuming that the dominant force is Ke. There is a reason for this. Let me analyze this with you. So this is, I think, the 6th page of us. So reason for validity of pure spring environment. In robotics, most of the time, the environment to be interfaced or interacted with, like this one or the surface here, is a hard contact environment. It's very rare that you come up with soft contact environments in robotics. So if you don't have soft contact, for hard contact environment, so majority of the environment types, let me say, are, well, let me put it this way, hard contact structures. What I mean by hard contact is this: Ke is much bigger than the environment damping. You can call it either DE or sometimes I call it as BE. So the environment stiffness is much bigger than environment damping, and that is further much bigger than the deflected environment delta M. So if we go back to our very first lecture note, here you can see the deflected environment. That's of course an exaggeration of the actual scenario. In reality, assume that I'm trying to push here with certain force. How much deflection I create? How many molecules can I press? And what's the total mass of the deflected environment? It's much less in comparison to the damping of the structure, and the damping is much less in comparison to its stiffness. It's really stiff, hard environment. So that actually tells me, I mean, this approximation tells me that in most of the cases, the pure spring environment model is valid for our applications. Of course, this doesn't mean that we don't need to analyze other scenarios. In the next video, I will be analyzing with you the environment model with damping also. But we will not move into the environment model with pure impedance, because that's called impedance control, and that will be covered under another video. So let me change the source. Well, okay. No, I couldn't succeed. Okay, guys. Today's first lecture was about the pure spring environment force control algorithm, and we have made the derivation. I'll try to also upload for you some simulations, some MATLAB Simulink simulations for all of you, where you can trace out the control algorithm. I'll try to implement this block diagram in a Simulink file and share it with you, so that you can also simulate it, or you can at least have a look at the responses under different scenarios. Thanks for watching.